Your cluster doesn't stay the same size forever. Hardware wears out and gets replaced. Datasets grow when you add nodes. A node fails and its data needs to move to healthy nodes. When these things happen, data needs to move between nodes. This process is called rebalancing. Rebalancing has a simple requirement: after it completes load, both data storage and query traffic should be fairly distributed across the new set of nodes. And it should happen without stopping the database. Users shouldn't notice. The most obvious approach to hash partitioning is to use hash mod n, divide the hash value by the number of nodes n and use the remainder as the partition number. Key 183756 on a 10-node cluster goes to node 183,756 mod 10 equals node 6. This approach seems clean until a node is added or removed. Go from 10 nodes to 11. Now key 183756 goes to 183,756 mod 11 equals node 4. Almost every key maps to a different node. Every record in the database has to move when you add or remove a single node. For a large dataset, this is catastrophic. Moving all the data causes enormous network traffic and I/O load. During the migration, queries may hit a node that no longer holds the data they're looking for. The migration can take hours. Your system is stressed and partially unavailable for the entire duration. This is why the book is explicit: hash mod n is a bad approach to partitioning. It was a tempting design, but it fails on any realistic change to the cluster size. The standard alternatives, fixed partitions, dynamic partitioning, and partitions proportional to nodes, all solve this problem in different ways, and each fits different systems best. The cleanest solution to the hash mod n problem is to decouple the number of partitions from the number of nodes. Create many more partitions than nodes, and assign multiple partitions to each node. When a node is added, it takes some partitions from each existing node. When a node is removed, its partitions are redistributed to the remaining nodes. The partitions themselves never change, only their node assignments change. This is called fixed number partitions, and it's used by Elasticsearch, RIAC, and Couchbase. Elasticsearch defaults to 1000 partitions per index. RIAC defaults to 64. Couchbase defaults to 1024. The book's illustration is vivid: if you have 10 nodes and 1000 partitions, each node holds 100 partitions. Add an 11th node, it steals about 9 partitions from each of the 10 existing nodes, ending up with roughly 91 partitions. The partitions that move carry their data with them, no other partitions are affected. The total data moved is 1/11th of the dataset, which is the theoretical minimum. The challenge with fixed partitions: you have to choose the right number up front. Too few, and each partition is large, rebalancing moves large chunks and recovery from a failed node is slow. Too many, and each partition is small, the overhead of tracking thousands of partitions per node becomes significant. If you don't know how large your dataset will grow, choosing the right number is genuinely hard. Dynamic partitioning solves this by letting partitions split and merge as data grows and shrinks. HBase, RethinkDB, and MongoDB use dynamic partitioning. In HBase, a partition splits when it exceeds 10 GB by default. The split creates 2 new partitions, each holding half the data. One stays on the original node, the other is transferred to a different node. When data is deleted and partitions shrink, adjacent small partitions can be merged. Dynamic partitioning adapts automatically to the actual data size. The limitation: when a database is first created with dynamic partitioning, there's only one partition, one node handles all reads and writes until the first split. HBase and MongoDB support pre-splitting, specifying an initial set of partitions so that a new database can use multiple nodes from the start. Both fixed and dynamic partitioning have a dependency. Fixed partitions depend on how many you created up front, dynamic partitions depend on the data size. Cassandra's approach cuts both dependencies by making the number of partitions proportional to the number of nodes. Cassandra and Ketama use a fixed number of partitions per node. By default, Cassandra assigns 256 virtual nodes per physical node. When you add a new node, it creates 256 new partitions and steals roughly 256 worth of data from existing nodes, distributed evenly across them. The total number of partitions scales with the number of nodes. As the cluster grows, partitions stay roughly the same size. The node design also handles heterogeneous hardware. If a new node is twice the storage capacity of the existing nodes, you assign it 512 nodes instead of 256. It receives twice as much data proportionally. The system adapts to nodes with different capabilities without any special handling. There's a practical benefit from splitting each physical node into many virtual nodes: resilience to hotspots during rebalancing. When a traditional single partition node fails, its entire data load moves to one other node. With nodes, the 256 partitions that lived on the failed node were already spread across many ranges of the key space, so the failover traffic distributes across many nodes simultaneously. No single node gets a disproportionate surge. The rebalancing question for any strategy is, how much human involvement is needed? The book distinguishes between fully automatic rebalancing, the database decides when and how to move data without operator approval, and fully manual, where an administrator explicitly assigns partitions to nodes. Fully automatic rebalancing is convenient but dangerous. A rebalance triggered at a bad time, disk failure, network congestion, can amplify a problem into a cascading failure. Couchbase, RIAC, and Voldemort generate a rebalancing suggestion but require a human to confirm it. That extra step costs time but prevents automated systems from making bad situations worse.